Graphs of polynomials. A polynomial is the sum of one or more algebraic terms that contain different powers but of the same variable. That would be something like x to the fifth plus 7x to the fourth minus x to the second minus or plus, I don't know, 8x minus 13, something like that. That's an example of a polynomial. Polynomial functions have continuous graphs, so once we put our pencil or pen down and start drawing, we don't pick it up until we get to the end, and they continue on forever. So really there should kind of be arrows here. They go on forever. They don't have any breaks in them. They don't have any sharp turns. They're all smooth curves. The degree of a polynomial comes from the highest exponent. So in this case, the degree of this polynomial would be degree 5. Power functions are functions where we don't have any extra parts to it, so it's just x to a power. So n is just going to be some constant, so like x to the first, x to the second, third, fourth, fifth, and so on. Those examples are shown here. These are the basic graphs that we tend to see. And if you notice, x to an even power will look similar to a parabola regardless of what that power is. And x to an odd power will look similar to a cubic regardless of what that number is. So what that's going to kind of take us into is something called end behavior, but we'll get there in a little bit. All of our power functions can be transformed using these transformations. So k on the outside is going to move us up or down, up if it's a plus, down if it's a minus, just like with trig functions when we did like sine and cosine curves. On the inside it's backwards, so left is going to be a plus sign, minus is going to be moving us to the right. And this out front is going to be a stretch or a shrink. Bigger the number, bigger the stretch. And if it is negative, that could flip us over. Okay, it'll be a reflection. All right, so here we have negative x to the third. So I can look at my x to the third graph, but all I need to do with that negative is flip it over. So it's just going to be upside down. So instead of down on the left and up on the right like I have here, I want to be up on the left and down on the right. For the next one, we have x squared plus 2. That's going to take my x squared function and move it up 2 spaces. So instead of being at the origin, I'm going to be up 2 spaces. I just want a rough sketch here. The next one, we have a cubic. We see we have the third power, but the minus 1 on the inside is going to move us to the right 1 space. So instead of crossing at the origin, it's going to cross at 1, but it'll still be down on the left and up on the right. We can do something called a leading coefficient test to tell us what to expect from our graph. So what that means is we are going to look at the leading term, and the coefficient is the number in front of that leading term, the constant we're multiplying it by. And its exponent will also be very helpful to us. So if we have an odd degree, meaning the exponent is odd, right, then we will have our ends going 2 different directions. If the leading coefficient is positive, I'm going to be down on the left and up on the right. For example, if I have 2x to the 8th power, right, odd, 7th power, so this is odd, this is positive, that's going to look like this on the ends. If I have negative 2x to the 7th power, then it'll flip. It's just a reflection. For even powers, say I have, I don't know, x to the 8th, why not? If we have a positive number in the front, like 6, then we're going to be up on both ends, just like a parabola would be. If I have a negative number, then it will be both sides down. So with an even degree, both ends do the same thing. With an odd degree, my ends do different things. So we want to look at this using our leading coefficient test to determine the end behavior. And our goal is to basically graph these polynomials. All right, so the leading coefficient, the whole leading term is right here. Technically, there is a 1. So this is positive, but we have an odd degree. Positive and odd degree is going to be this first option here. So it'll be down on the left and up on the right. So we write this as a nice, pretty way. We'll say that the limit As x approaches negative infinity, that would be referring to this one on the left as we move towards the left, the f of x, or the y value, is going down. So it's going to give us negative infinity. Okay. On the right side, the limit as x approaches positive infinity, f of x is going to give us positive infinity. So on the right, as we move to the right towards the x's being positive infinity, the y's are moving towards positive infinity. All right, for the next one, we see we have the 2, which is positive, and the 5, which is odd. So positive and odd, we're going to have the same thing here, down on the left, up on the right. So this is the limit as x approaches negative infinity, that means the left. F of x is approaching negative infinity, that means down. The limit as x approaches positive infinity, that means right. F of x is approaching positive infinity, that means up. Okay. For the next one, we have a negative in the front, and we have an odd. So that means they're still doing different things, just flip-flopped, up first and then down. So on the left, the limit as x approaches negative infinity, f of x is going up, so it's going to approach positive infinity. As x approaches positive infinity on the right, f of x is going down. Okay. And then one more. We have, let's see, we have x squared, negative x squared, sorry. So that's negative in the front. That's even. Even does the same thing. If it's even positive, it's up, but it's negative, so they're both going to be down. So the limit as x approaches negative infinity, that means left. F of x is going down. That means negative infinity means down. The limit as x approaches positive infinity to the right, f of x is also going to go down. Okay. So if you notice the limit as x approaches, that part's the same every time. This part looks the same every time. It's just a question of what is the y doing on the left, what is the y doing on the right. We can get zeros of our polynomial functions really by factoring. We're really using our Algebra 1 skills. We're going to set the polynomial equal to 0 and find the zeros, hence the name. So we have x squared plus 4x plus 4. We can set that equal to 0. And if we can factor, we should. That's x plus 2 times x plus 2 is equal to 0. That means using the zero product property, x plus 2 equals 0, but also so does x plus 2. And we're going to get negative 2 for both of them. Okay. X squared minus 9, we'll set that equal to 0. That is a difference of squares. That's x plus 3x minus 3. So x plus 3 equals 0 gives us negative 3. And x minus 3 equals 0 gives us positive 3. So we have 2 intercepts there. All right, the next one we can do by grouping. So I'm just going to kind of start us off there. Equals 0. We'll factor out the GCF from each group. We get x plus 3 times x squared minus 4 equals 0, which can factor again. X plus 3 times x plus 2 times x minus 2. And you could probably even take a look at this without doing too much more work and seeing to get 0, that's going to give us negative 3, negative 2, and positive 2. And then lastly, we do have a GCF on this, so that's x cubed. That's going to give us x squared minus 1, and we can factor that one more time. So we get x cubed equals 0, which is just 0. We get x plus 1 is 0, so negative 1, and we get x minus 1 is 0, and we get 1. Okay. So knowing our zeros is going to take us one step closer to getting a quick sketch of our polynomial. We can have repeated zeros. We saw that happen here where we had x plus 2 and x plus 2 giving us the same answer, so we only had to write it once. Here, technically, we have x equals 0 written 3 times. So we can have repeated zeros. And what we talk about is their multiplicity. It's telling us how many times it is being repeated, how many times it is showing up. If our multiplicity is odd, then what's going to happen is at that spot on the graph we're going to cross over the axis, whether it's that way or this way. So if it's an odd multiplicity, we're going to cross. If it is a even multiplicity, if k is even, what's going to happen is we are going to bounce or just touch it, or some people will say kiss the axis. And you'll just kind of go along, do whatever you're doing, and you'll touch it and come right back up. Or it could be from the other side. So you touch it and just go right back down. Okay. So our multiplicity is going to help us to graph our picture. So we're going to find the zeros and then figure out the multiplicity. The multiplicity is based on exponents. So here we have an exponent of 3. This has a multiplicity of 3. So you'll see that in just a second. All right, so it's already factored, makes life easy. We have x minus 1 equals 0. That had a exponent of 1. So that's going to give us x is 1 with a multiplicity of 1. We have x plus 2 to the 6th power equals 0. That's going to be a multiplicity of 6. That comes from this. When we solve this, that's x equals negative 2. Okay. Over here, we have x equals 0. Technically, that's the first power. So that's a multiplicity of 1. We have x minus 3 squared equals 0, which means we have a multiplicity of 2. So that's going to give us x equals 3. And we have x plus 3 technically to the first power equals 0. So it's going to give us x equals negative 3 with a multiplicity of 1. Okay. And then lastly, we have 1/4. We can't do anything with that. X plus 1 to the 5th equals 0. That's a multiplicity of 5. So x equals negative 1. I'm just setting the inside equal to 0. 3x minus 2 squared is equal to 0. That's a multiplicity of 2 from that exponent. We'll add the 2, divide by 3, so we're going to get 2/3 for our intercept, or our 0. One more thing I just want to note is that if x is equal to a, that means it's a 0. X equals a is also called a solution to the polynomial. Then if we switch the sign, x minus a becomes a factor. Notice when I have x plus 3 as a factor here, negative 3 is a 0. And then it's also an intercept. So if I just put a comma 0 at the end of it, that's what makes it an intercept. All right, we can find a polynomial function if we are given the zeros. So what we're going to do is kind of use that same concept, that if a is a 0, then x minus a is a factor. Okay, so that means that if these are zeros, x minus those numbers are factors. So I have x minus a half, or minus negative a half, sorry, so that'll be plus. I have x minus 3, and I have x minus 3 again, so that's going to be squared. The only thing we should do is FOIL this out to get an actual answer here. So we have x plus a half. We have, that's x squared minus 6x plus 9, and then we'll FOIL one last time. X cubed minus 6x squared plus 9x plus 1/2 x squared minus 3x plus 9 over 2. So that's going to give us x cubed minus 5.5 x squared plus 6x plus 9 over 2. And we can do the same over here. So we have x minus 2, x minus minus 4, and x minus 5. And again, we're just going to FOIL this out. So that's x squared plus 4x minus 2x, so plus 2x minus 8 times x minus 5. So we get x cubed minus 5x squared plus 2x squared minus 10x minus 8x plus 40. And we'll finish that up, x cubed minus 3x squared minus 18x plus 40. Okay.